Hello, my name is Aurelio Reese. I'm the Director of Graphics Tools at NVIDIA. I'm here with Jeff Keel, Engineering Manager. So today we're going to talk to you about some of the tools that we've been working on. And the point of our tools fundamentally is to save a lot of time and frustration, and how we have spent a lot of time and effort to make sure that we can enable developers to make the best games they can. So we're going to cover a few topics today. First, I'm going to give you an overview of our Graphics Debugger and Profiler, Insight Graphics. Next, Jeff's going to give you a demo and show you the tool in action. And after that, we're going to wrap up with some key takeaways and a Q&A. So before we begin, can I get a show of hands? How many people have used Insight VSE, Visual Studio Edition? Oh, wow. That's a lot. Great. How many people are currently developing their application in DX12? All right. DX11. Vulkan? Oh, look at that. OpenGL. Wow, all right. Glide? GL? No? All right. I was just making sure you're paying attention. That was a lot of hands, actually. Okay, so let's dive in. So the story so far, Visual Studio Edition has been out for almost 10 years now. And that's obviously been a great opportunity to develop a lot of great features for developers and bring a lot of value. If you're not too familiar with it, fully integrated into Visual Studio IDE. It's Graphics Debugger, Graphics Profiling. It also has compute profiling and debugging via CUDA. And like I said, over 9 years of learnings, it's given us an opportunity to learn a lot about shader debugging, to learn about the APIs and a lot of the issues that developers face. And so, depending on who you talk to, it's an ideal workflow because you're in the place that you're writing your code, right? But there are some caveats. It's reliant on the Visual Studio ecosystem. So when there's a new Visual Studio version, we have to adapt to that. There can be interactions with the plugin infrastructure that can cause issues. We have to make sure that we guard against that. And also, because we have this compute component, there are dependencies on that for release. So we have to make sure if there's a new CUDA version, right, we have to align our releases to that. So we asked ourselves, what can we do to improve? We talked to developers very regularly. We wanted to make sure that we were listening to you and improving on the things that you have been asking for. And so that's where Insight Graphics comes in. Insight Graphics is the newest tool from NVIDIA Developer Tools, and with it we hope to continue to improve developer productivity by providing something that you've been asking us for a while, that standalone version of Visual Studio Edition. So it's standalone, fully featured debugger and profiler, DX11, DX12, Vulkan, OpenGL. Live capture and replay, you can serialize your captures to a C++ file. We'll talk about that a little bit, and Jeff's going to show you what that means. And there are just numerous debugging features for tracking down hard-to-find bugs. When you encounter a graphical issue in your game, it's really the best tool that you can use to try to find why that is. And one of the key things about our tool is its advanced profiling functionality. We give you unprecedented access to NVIDIA hardware. And so when we said that we wanted to do this, we kind of went to the drawing board and we thought, well, what are the key things that we want to reinforce by building this tool? And so we defined these key pillars. And fundamentally, we're a pretty good graphics debugger. We have optimized replays that doesn't have any engine overhead, so you can save your frame to disk, get a C++ project out of it, hit F5, and you have an executable that you can basically relaunch for profiling because your engine's not actually running at the same time. You can share that executable with someone. You can run additional experiments within the future. There's C++ codes. You can just go edit the C++ code, enable branches, add anything you want, modify resources. It's incredibly powerful. Shader editing, so you can find those hard issues with your shader and be able to actually go in there and run experiments to change things. Pixel history, resource viewer, geometry viewer, API inspection. There's a tremendous number of things, and Jeff's going to go into that and show you what that means. The other thing that, and I would almost say is a key pillar for us, is the profiling support that we offer. We understand the hardware very well, and that affords us the ability to build a profiler that really lets you get really low-level detail. So the range profiler is something that we've had for a really long time. A lot of great information you can get out of it. Hardware performance counters. There's shader stats so that you could see how many instructions you have for all the shaders in your scene. You can compare them side by side. Event timings, metrics selector, API stats, a tremendous number of things. And something brand new that we're bringing with Insight Graphics is something we're calling GPU trace. GPU trace, there's a picture of it here, actually allows you to analyze the GPU occupancy of your frame. And in addition to that, it shows you if you're using DirectX 12 or any language or any API that has this capability, it shows you asynchronous compute, both in action and then opportunities for where you can add that. Jeff's also going to give a great demo of that and kind of go in depth into how useful that is. And then finally, RTX was announced at the show. It's the basic ray tracing acceleration stack that enables something like DXR to exist as an API. And so that's incredibly important to us. We see that as the future. We committed to spending a lot of time to building a good debugger for that. So as of today, you can actually debug DXR applications with Insight Graphics with the caveats if you have the right driver, all the other conditions, RS4, that kind of stuff. But we have DXR samples on our website. You can go download them, try it out, attach the debugger, step through it, look out for that dispatch raise call, and learn. There's a great blog post about DXR and RTX on the website as well. Definitely check it out. But the things we bring to that are that basic debugging support, and then shader bind table inspection, so that you can actually see when you do your raycast into the scene, you can actually see all the shaders that are run based on what's hit. And so fundamentally, what it comes down to is we believe in developer choice. We want to make sure that all the developers are able to find the best workflow that works for them, and we want to reinforce an ecosystem where they can build on our GPUs and have a positive experience and do it as fast as possible. So the big thing there is Insight VSE, Visual Studio Integration, the compute tools, tracing tools. If that coincides with your workflow and the needs of your project, perfect. You have something great there. We're going to continue to support it. There's updates coming out that's going to include a lot of great functionality that's also going to exist in Insight Graphics. Insight Graphics, we're looking to improve upon the model that we built and have more frequent releases so that you guys can see the new features quicker, fixes. Developers talk to us often about issues they're encountering. We're really quick to get on top of that and provide those fixes. Activity system, which is effectively a plugin system that allows you to define a workflow. Are you going to be doing debugging, profiling, GPU tracing? And then advanced profiling. So GPU trace is an incredibly powerful way to understand your scene's performance and have actionable data that you can actually go and take and be able to improve your game's performance, and ultimately to allow you to have even higher fidelity scenes. So I'm going to hand it off to Jeff Keel, who's going to give you a demo.
Great, thanks very much, Aurelio, and thanks everybody for joining us today. I'm going to start out with a quick tour of what's inside of Insight Graphics. For those of you who have had the opportunity to use Insight Visual Studio Edition, I think a lot of this will look familiar, but obviously we've been working really hard, literally around the world, and quite often around the clock, in order to kind of bring these new features to you. One of the things, obviously, is that now we're in a standalone shell. So no longer are we bound to using Visual Studio. We had feedback from developers that they don't necessarily have a license for Visual Studio on all the different systems. They want to be able to use the tool. So that's why we decided to go ahead and put this in an independent shell. Now, also note that all of this code is exactly the same stuff that we share inside of Insight VSE. So as we go ahead and add improvements to one or the other product, they will automatically show up in the other. So don't feel like you're like, oh, well, I'll use Insight VSE for this and Insight Graphics for that. They'll have a lot of parity in terms of their feature capabilities. So one of the great features that we added for Nsight Graphics is the ability to kind of set things up from your project's perspective. So we do have a basic project system and also some artifact management, which is really nice. Before I get into that, there's some other capabilities that allow you to kind of get things started really quickly if you don't want to go through the entire project system. So you can actually do a quick launch, which will basically just give us the path to your executable and give us some of the settings you want to have, and you can just launch your application. You can create a new project, and obviously you can load a project from somewhere else on disk. I'm going to go ahead and load the Hellblade project. And we want to give thanks to our friends over at Ninja Theory for allowing us to use Hellblade to do some of our demos today. And basically, once you start that up, you're going to have your connect to process dialog come up. In the upper left-hand corner, you're going to select your target platform. Now, right now, it's kind of boring. It only has Windows. But you can imagine where we're going to go with this. We're looking to support Linux in the future and things like that. So we want to be able to bring this same experience across all the different platforms that you can use NVIDIA GPUs on. Once you select your platform, you have a number of different activities that you can select. The frame debugger activity is going to be where you do all of your API debugging. So that's where you're going to spend time trying to figure out how am I utilizing the GPU, what are my settings, what things are bound, things like that, just to be able to figure out where those anomalies might be happening because of your setup of the GPU or setup of the API. Then you also have a frame profiler activity. Now, the frame profiler activity is going to basically launch the UI with a frame profiling centric view. Doesn't mean that you can't necessarily do some of the same things, like for instance, you can use the same scrubber, you can use the API inspector, all those types of things. But what's going to happen is your initial settings will look very much more like a profiling session than a debugging session. And obviously those two are separately persisted. So now if you have certain windows and certain layouts that you like when you're profiling, that can be more of your profiling side as opposed to your debugging side. The next one you can also do is you can just do a generate C++ capture. I really hit on this earlier during the intro. The idea here is that when you capture a frame, and we do these live captures, right? So it's not just simply do a binary file somewhere and you have to look at it later. The capture is live. You're actually able to interact with your application on the fly. But you do have the ability to save those off. And this is a quick way to simply save off a number of different captures, and it allows you to quickly compile those, and they'll show up as artifacts over here in our Project Explorer. So it's a really nice way to be able to collect a number of different frames that you want to look at for different debugging capabilities or different profiling. And the other thing you can do with the C++ captures is, most of you I'm guessing are programmers, is you can make edits to them. And so if you're finding a bug maybe and you want to say, oh, well, maybe I just need to change this setting or rebind this texture in some different way or whatever, you can try it out in the C++ capture, kind of do a proof of concept. Then you can go back to your engine, and make all the mods you need to do, which are probably going to be a lot more involved. Finally, one of the latest ones that we've just added, and this is still in preview, it's not quite going to be released, and actually 1.0 just got released this past Monday. Unfortunately, it does not include GPU trace yet, but I'm going to go show you guys a preview. And GPU trace allows you, again, to look at all those SM utilization. So it gives you an idea of how much you're using the shader units inside the GPU and kind of see that balance across the different types of workloads, see how you're utilizing async compute and things like that. So what we're going to do is we're going to start out with a frame debugger. Oh, I meant to mention these over here. So over here you can select which device you want to run on. We actually have a little application you can run on remote systems. So if you want to launch your application on a remote system, that's fully supported. Then you have the ability to specify what your application executable is, the working directory, obviously any command line arguments. Also new with this is you do have environment variables. So if you have to have special environment variables set up in order to be able to run your application, you can specify these here. And there's some additional options. We won't go into those. All right, so I'll go ahead and launch. And it's going to look very similar to those of you who have had experience in Nsight Visual Studio Edition. You can see here that in the upper left-hand corner, this is our status bar. This is kind of our real-time HUD that gives you feedback on what's happening with the application. And we have our batch histogram over here. And you can double-click the batches and everything like that. Again, if you've used Nsight Visual Studio Edition, this will all look very similar to you, or familiar to you. And then you can hit spacebar, and that's actually going to capture the frame. Now, you're probably noticing that she's not moving on the screen. That's because this is one of those serialized C++ captures. It just makes demoing life easier to reduce the number of variables and what's happening in the scene. So again, similar to what we've had in Nsight VSE, you've got the ability to scrub through your scene, so you can watch as all your different draw calls are going to be landing to the various render targets. We've got a little bit of shadow pass going on there, doing some lightings. Now we're going to do our gbuffer pass. And you can also do things like you can select which render target you want to look at. So you can select any one of the render targets. You could do normalization of the render targets, all that kind of stuff. So it's really, really rich in terms of its ability to be able to debug what's happening in the scene. And we also like this because it's a really speedy scrubbing experience. You can see here I can move my mouse very quickly, and it's a very nice and speedy scrubbing experience. And so the idea here is that you'd probably use the target in order to kind of find where that initial bug is, where that initial thing that you're trying to debug is. And obviously we show exactly which geometry is being rendered. Look at the hair and things like that. You can also look at the preview textures and everything. So again, all those same things you had in the HUD in Nsight Visual Studio Edition you've got right here. So now let's go and shoot over to what's happening inside of the host. So inside of the host, similar to the target, we've got that scrubber up there. And so you can kind of scrub through and everything like that and visualize things. We've got your current target view up here in the left-hand corner, kind of show you what different render targets are currently bound. You can select, again, different render targets and visualize those, and it shows what your post-transform geometry looks like. In the lower left-hand corner is our events view. The events view is really powerful because this is kind of like your connection to your engine, right? You've got all this code in mind. You made all these different, state settings and bindings and draw calls and dispatches, and this is the connection to your code. So it allows you to say, okay, what does my trace look like across the entire scene? And you can look for anomalies. You can look for things like, well, let's, give me an example. I'm going to say PS set shader and draw call. So now what I'm going to do is I'm basically going to filter this based on how many times I call PS set shader, how many times I basically change the pixel shader versus how many draw calls I have. And this could be a potential problem in your performance because the more times you change the shader, there's basically only a certain number of shaders that can be in flight in the GPU pipeline at any given moment. And so if you're frequently changing your shaders, you could potentially cause a stall because they basically have to wait for all the rest of the work that's currently in the pipeline to exit out before it can change that shader. So you can see here in the beginning when we're doing things like our shadow passes and our G-buffer passes, we're not changing those shaders too often, and we're doing a whole bunch of draw calls. But you notice here towards the end, we're actually going to start to see a little bit more thrashing, a little bit more, maybe 2 or 3 draw calls, and even here we got a section right there which is like set shader draw, set shader draw, set shader draw. So again, it's even a great way to just kind of look at your scene, look at the call event list, and be able to say, okay, how am I doing with the API? Am I abusing the API, if you will? We also have some predefined filters in there. You can look for things like look for all the calls that have a GPU time of greater than 0 and things. So you can kind of have those quick ways of being able to search for different elements that you're looking for. In the lower right-hand corner, we've got our API inspector view. Our API inspector view is basically going to give you all of the current settings for that draw call, basically the state of the API at that moment. In the upper left-hand corner of the API inspector, we show you kind of a virtual GPU pipeline and give you a feel for where all those settings are going to impact things inside the GPU. So you start up at the top at the input attributes, and this is where you're going to see all the information about what your input layouts are, what your vertex buffers and index buffers are, their different formats, things like that. It even has links to those resources, which we'll talk about a little bit more when we get to the resources view. But everything is fully connected. Again, same as Visual Studio Edition. You just click on a buffer link and you just instantly go over there rather than having to kind of remember things in your head and then go to some other view. Everything is nicely connected there. Then you come down to your shader units. These are all going to look very similar. So you have basically all of your information in terms of what your current constant buffers are, format information, again, links to those in the resources view, what your sampler information is. These are your tessellation shaders. We're not currently using those. But you've got rasterization state, so your cull modes and all that kind of stuff. So just being able to check those settings. So like, for instance, if you're doing your shadow pass, you want to make sure, obviously, that you've got your depth set up properly and you've got your rasterization mode set up properly. Again, pixel shader, we're going to look at very similar stuff that we had in the vertex shader, but now we actually got all of our input textures that are bound. So we can kind of see those at a glance. And finally, an output merger. That's where we're going to see what all the different render targets that are bound, what my depth stencil state is. Again, when you're doing your Z passes, make sure that you've got your color masks turned off and your writing turned on, your Z writing turned on. Just checking that state, making sure that everything is set up exactly the way you need it to be. Next, we've got our resources view. I'm going to click one of these output targets. I'm going to open up the resources view. And the resources view is basically a rich way to look at all the different resources you've got bound in your scene. So you can see here we've got everything from some of the resources that we're actually using during our loading of the capture and the restoring of the capture. And then you've also got all the different textures and cube maps and all that. Down here you've got all your different buffers that are going to include your index buffers and vertex buffers. And we've got a number of different ways that we can visualize that. When you choose a render target, obviously, or a texture, it's going to be a nice, rich graphical visualization. You can use the mouse mouse wheel to zoom in and all that kind of stuff. And we've got the nice little histogram over here, so you can do some basic remapping of the colors and everything. That's really helpful with like depth buffers and things like that, or maybe like R channel only buffers. Then we also have a memory view. So now you can basically come over here and grab one of these buffers, and you can say, okay, it looks like these are going to be float values. So put that to 32-bit float, and you can look at your constant buffers and things like that. You can also look at those in your API inspector. I didn't touch on that when I was there, but it's a nice feature to be able to kind of in context be able to look at those. All right, the other feature that we have, or a couple of the features that we have, on the lower left-hand corner is your basic information in terms of your view information. So obviously you could have a given render target or texture or UAV that has a number of different views on it, so you can visualize those. And you can see all the information in terms of what's the settings of it, what the flags are and everything. Then we also have all the different revisions of the buffer. Now this is really, really helpful because it shows you how this buffer was kind of constructed in the scene. And in some ways it's almost like another version of a scrubber. So you can kind of watch as the draw calls happen throughout the scene, and we kind of give you these little thumbnails, and you can use this to go, oh, okay, that section right there, yeah, that piece of fence right there, maybe that's where my bug was. So it's a nice way to be able to kind of hone in on where your bugs might be. Now, the other thing you can do from here is you can actually kick off a pixel history. Now, this is a new feature that we added about a year ago, and you can basically, and we support it on DX11 and OpenGL. But I can come in here and, for instance, let me choose a piece of this rope so we actually get something somewhat interesting. And I can choose a pixel right there. It's going to run a pixel history, and it's going to give me an idea of all the fragments that contributed to this. Now, there's a couple of different ways you can visualize this. When I click this button, this is basically going to be only the ones that have actually landed in the frame buffer. Now, they could be, later in Z, and therefore they might have been blended away or something like that. But these are all the ones that landed in the frame buffer. Now, if I click this back on, this is actually going to show all the fragments, including ones that never landed in the frame buffer. So maybe they were early Z'd, or maybe it was backface called. And you can see here that, like, for instance, we've got 3 in this draw call right here that were backface called. So these 3 right here. And that's really important because you could be saying, like, I'm expecting this big orange thing from this, piece of cloth or whatever, and I don't see it. Why not? Oh, well, you can see right now, not literally, I got lucky to mention orange, but we got this orange pixel right here. Oh, it was backface called. Oh, okay. That makes sense. Now I know I've got maybe my winding order wrong or something like that. And you can use that to go over to that draw call, figure out what your winding order is, and maybe that'll help fix your bug. But the other thing we show you is basically what your render targets looked, the color at that fragment, at that pixel location looked before, the color of the actual fragment that was blended, and then the color afterwards. And we show you that basically for all the different fragments that you see. As well as, again, a quick little preview of what each individual draw call did to all the currently bound render targets. And then also, again, these are links. So this is going to link back over to the resources view and show you exactly which draw call you were on and everything. So it's a really great feature to be able to kind of dig in on your different fragments and figure out where any issues might be. All right.
Filtering.
Sorry?
Filtering. Filter resources.
Oh, sure, I can talk about that. So another capability we have is the ability to do a couple of different filtering. So one thing you can come in here is you can come in here and just look for textures or whatever. But you can also have some predefined filters. So I can look for maybe some larger resources, some resources that are unused. This is really helpful because you could have some situations where, this is unused in the frame, you could have some situations where you've got some resources that are not necessarily being used in that frame. Now, it could be that they're used in a previous frame or a later frame, and your engine hasn't exited it, kicked it out from the cache. Or it could be a problem that maybe your content pipeline has some resources there that are that you don't necessarily need to use. Then we also have a number of different visualizations here in the details section. So in the details section, you can basically see a table of all the information, and you can sit there and sort based on format or sort based on size or the amount of memory used, and again, look for those larger resources and everything. All right, so now what I want to do is jump over to some DXR debugging. So for those of you who probably have heard, DXR is the latest API from Microsoft that allows us to do ray tracing in kind of real-time graphics, which is super, super exciting. And we obviously have our core ray tracing technology, as Aurelio was saying. We've got our RTX, which is basically the underpinnings and how we have implemented DXR for DirectX 12. And so I've got an application here. It's basically just a little sample that we wrote here at NVIDIA to show you how to do basic ray tracing and everything. And this is really great because we went ahead and tried to do some implementation of some features to help support you when you're doing this initial, ray tracing development. Specifically, we focused on some of the debugging capabilities because we know, like, the first thing you do is I just got to get a pixel up on the screen, and I'm not sure why I've messed it up. And so we wanted to focus on the debugging to start with. And so I'm going to do that same thing. Just hit Control-Z and spacebar to capture the frame, and you can see we've got a nice little, office scene that's ray traced. It's got some nice reflections here in the floor and everything like that, and nice shadows and things over here. And so again, we've got our normal scene here, but I want to focus in on some of the stuff that we have for specifically for ray tracing. And so I'm going to look for my dispatch rays call, and this is the call that you basically do to kick off that initial set of rays that are basically going to represent all the rays that are coming from your eventual render target. And your first shader that's going to happen is your ray generation shader. Now, what this is going to do is this is going to be the thing that's going to figure out, basically generate all of those rays. It's going to be the shader that's going to declare where all those rays are going to go. And you can see here we've got the ability to look at the different shaders that are bound. I can even click on the shader itself and look at the actual shader code. I've got all the root parameters and everything and root arguments. But then also I've got all the other shaders. So I can look at my mist table, for instance. I've got a couple of different mists. If I've got a primary mist or a shadow mist, I can look at the different root parameters that are bound for each one of those different shader types. And then I can look at my hit table, and I can all the different types of hit shaders I've got. So I've got primary versus secondary versus shadow and all that. So I've got all these different shaders that are bound, and I can visualize those really nicely. The other thing we can do is you can see, again, all those different buffers that are bound. Actually, I want to go over here and go up here, close that off, and grab this one right here. And this is basically the SRV for what's going to be eventually rendered, or sorry, the UAV for what's eventually going to be rendered to. And again, everything's completely connected. So I can grab that resource that's bound there and inspect it right here. And again, any other of the resources that are there, they're going to be fully connected with everything that's here over in the resources view, where you can kind of do a much more in-depth analysis of what's happening inside the resource. Alrighty, let's go ahead and jump into some profiling, because everybody loves to find out how to make their code and their apps go faster. All right, so I do want to give a shout out to Louis Bavois. He's actually going to be doing a talk right following this talk on how to do performance analysis. And basically the genesis of the talk that he's going to give started from a blog post that he put out called Peak Performance Analysis Method for Optimizing Any GPU Workload. So he did an amazing job with this. It gives incredibly great tips in terms of how you can utilize the tools in order to figure out where your throughput is limited for your scene, and really gives great information on how to analyze the data that comes out here. I'm going to give you kind of a quick overview, but again, if this is something that you really want to geek out on, definitely hang around for Louis' talk, because he's going to go in depth on a bunch of different ideas. So the basic profiling methodology is, first and foremost, you want to start with a repeatable test case. It's the old thing where, if you're tweaking too many things in between, it's just not going to be possible for you to be able to really figure out if a given improvement is going to result in a decreased frame time or an increased frame rate. And so that's one of the things that those C++ captures are really helpful for. So you can go ahead and serialize that frame, compile it, and actually you can compile it right here from within the tool. You don't even have to shell out to Visual Studio. We go ahead and build that using MS Build for you. And then what you want to do is, once you got that repeatable test case, now you want to start to figure out, okay, first question is, am I GPU bound or am I CPU bound? There's a number of different ways that you can do that. First, you can use Nsight Visual Studio Edition and use our analysis tracing. What that's going to do is going to give you a frame, basically a layout of your frame, and give you an idea of how what your workloads look like on the CPU and on the GPU. And specifically, it's going to look at all those different command buffers that are being submitted to the GPU. And basically, you're going to want to look for gaps inside of that section to figure out, okay, where am I not utilizing the GPU? And that's going to give me a feel for, if I've got a lot of them, I'm probably not nearly as GPU bound as maybe I think I am. Another way you can do it is, here from within Nsight Graphics, you can graph the GPU busy percentage counter or metric. And basically, if you're in the 95 or plus % range, you're edging onto, if not fully GPU bound at that point. So that's kind of a quick rule of thumb. If I'm 95 plus % GPU busy, I'm probably going to be GPU bound. The other thing that probably a lot of you folks out there have already done is you've probably done some level of hand instrumentation inside of your application, right? You've got some basic queries that go ahead and give you the timings on the GPU. You obviously know what your frame rate is on the CPU. And so you can kind of compare those two. And basically, if your GPU time is, greater than or equal to your CPU time, that means you're probably going to be GPU bound. So once you figure that out and you know you're GPU bound, obviously you're CPU bound, there's plenty of great tools, Intel, AMD, they've got awesome tools out there to be able to do that. But when you're GPU bound, you need to come into Nsight Graphics to be able to figure out, where am I spending all this time? All right, gave myself away right there. All right, so the first thing we want to do, and again, Aurelio touched on this earlier, is I want to show you the brand new tool that we've got in terms of GPU warp trace. Or GPU trace. So I don't want to actually show you how to do the trace. It's kind of boring. You just basically, start the application, wait till it starts, and then hit F11, right? So not that interesting. It's much more interesting to look at the resulting data. So this is an example from Claybook, which was given to us by the second order team to allow us to use for the demo. And now I want to emphasize that this is not their problem. So we did a trace of their application, and I mucked with their trace. Kind of like I talked about earlier, you can improve things. Well, I actually made things worse in their trace to be able to give you guys an example of what you can look for. And so the idea here is that we're looking at this graph up here in the upper left-hand corner. We're looking at all of the warps, or basically groups of threads, as they're being executed on the GPU. We've got these color-coded, so you can see here's my yellow, which is my vertex work, my green work, which is my fragment work, and my kind of salmony pink color, which is my compute work, that's actually happening on the direct queue. So this is compute that you're submitting on the direct queue in the frame. And you can see here that across the frame that, I'm never really reaching a pretty high level of GPU utilization. The idea here is that this is the entire GPU. So basically this is giving you an idea of how many warps you can have active inside the GPU. And you're probably not going to reach 100%. Really, if you reached 100%, you'd probably be thrashing your caches so much because you've really got too much work to do. But you want to be probably in the 50 to 75% range. And that's probably going to be a really good balance between your GPU, your SMs, your shader units are occupied, but they're also not thrashing all the rest of the resources and actually hurting your performance. Down here, we actually show you a balance across all the different subunits inside the GPU, so all the different sub-shader units inside the GPU. And then down here, we show you all your different markers. Again, if you're not using perf markers, either user annotations or D3D perf markers or whatever, please annotate your applications. It makes things so much easier when you're looking at things like GPU trace and the range profiler. But these are your different markers, and you see we've got two different queues. They're both direct queues in this case, and we've got our what was typically our direct queue information here, and then we've actually got some compute happening only on this queue over here, and that's obviously a hint already. I've got some compute that's only happening on one queue. Maybe I can try and actually have those go off simultaneously and actually achieve some async compute. We also show you what all your different actions are, which are basically going to, again, be your draw calls and your dispatches. Then over here, when you've got a selected range, we show you kind of a breakdown of what's happening inside those shader units. So over here on this top section, we're going to show you which warp types are active. And again, warps are basically 32 threads that are going to be running the same program. And we show you a balance in terms of what your vertex work is, what your fragment work is. So if I select, this render section right here, you can see here it's about 28% of 28% of the time I'm spending on fragment work, 28% of the time, and then about 71%, 72%, I'm basically unoccupied. So again, that's another one of those sections that I could potentially look at to be able to better utilize the GPU. And then down here is basically an overall SM active time, or shader unit active time. So it gives you a feel for how busy it was using graphics versus compute versus asynchronous compute, and then how often it was idle. The last thing I want to point out is this row right here, and this is the graphics idle row. And the important thing here is that this is going to show you the difference between when the shader unit, which is, I'm going to use a gross term, the middle of the GPU, where the shader unit is versus the rest of the units inside the GPU. So anytime you see this value going up high, that's a time when basically there's not any work going inside the GPU at all in terms of the graphics pipe. That could be a time when you're maybe doing a copy, but it could also be a time when you're just working on some CPU workload. The GPU's crunched down all the stuff you wanted to crunch down on, and it's able to continue. But this is a section over here where basically we've got a time where we've got some work in the GPU. It's just not necessarily in the SMs at that moment. So that's going to potentially be doing some blending or maybe some setup to trying to set up some draw calls before it actually sends them down. It could also be a stall that it's basically waiting for things to drain out of the bottom of the pipeline before it can kick off, for instance, that compute work. So that's going to be able to see what you see there. All right, so come back here to the top, and we can see again that I've got not a whole lot of asynchronous compute going here. So what I want to do now is, for those of you who know how to do compute queues, this will be a little bit old hat, but basically the idea is you want to go ahead and construct a queue that's got the command list type compute, and obviously you want to make sure that all your command lists and all that kind of stuff are constructed with that similar flag. And then what you can do is now you're going to see what I call the bad async. So the idea here is that now I've got two queues, and again we've got, or a compute queue I should say, we already had two queues. And you can see here, but the problem is I don't have any overlap here. So I've got, a bunch of stuff happening on the direct queue, and then a bunch of compute, and then a bunch of stuff direct queue, and a bunch of compute, and so it's getting there. It's kind of good that, I'm at least getting two queues and all that kind of stuff, but obviously I'm not getting any parallelism here. And you can see here, I didn't mention this earlier, but you can see here my frame time didn't really change much. As a matter of fact, it might have even went up just a hair. That could be because of the two queues. That could just be noise, in the measurement. But we can see here that I haven't really achieved what I'm looking for, which is some great asynchronous compute. Well, the good deal is that I can actually use the tool to try and figure out, okay, why am I not reaching that asynchronous compute? So what I'm going to do is I'm going to come in here and run my frame debugger. Launch the application. And this is actually a multi-frame trace. Shh, don't tell anybody we do have that capability. We just haven't introduced it into the tool yet. And that's why you see this flickering over here. I'm going to capture a frame. And then I'm going to go over to the tool. And one of the things we show you, especially in DirectX 12 and Vulkan, is all your synchronization that's happening in the scene. And you can see here I've got times when, I've got graphics work happening on, actually, I used the wrong parameters here. Sorry about that. Let me fix that real quick. Come on. All right, there we go. There we go. And actually, I want to show you one thing while that's starting up. The reason why this is important to be able to have multiple queues is when you have a direct queue, your game is basically going to be submitting a bunch of command lists with either graphics, compute, or both. And the idea here is that there's a level of guarantee that the API gives you that these are going to happen sequentially on the GPU. It's basically saying anything you put in here, this work is going to complete, then this work, and then this work, and then this work. You do hit a little bit of overlap in between if the GPU can, but in general, there's a little bit of synchronization there that's happening. But what the compute queue allows you to do is basically a hint to the driver and to the GPU to say, hey, this can be scheduled at the same time as here. I've gone ahead and taken care of any synchronization you need. So if you have room on the shader units, please do go ahead and schedule that at the same time. So that's why you really want to be able to use that. All right, so we'll go ahead and capture that frame. All right, there we go. That looks better. And so you can see here we've got our graphics queue up here, and then we've got some compute going on, and then we've got some synchronization happening like right here. Here's a great example. So we've got some graphics work right here, we've got this synchronization right happening, and then we've got this compute work right here. And so we've got this thing where we're basically saying, okay, I'm going to do this graphics work. When it's finished, I'm going to go ahead and fire off a signal, and then it's going to go ahead and wait on the graphics queue, and then it's going to wait for that signal, and then it's going to fire off that work. And that's the problem here, is I was not very good in terms of getting my asynchronous graphics set up. So I went in there and I went ahead and removed all those. Terminate. There we go. I went ahead and removed all those, and now I've got my working async. And you can see here that, great, so I've got some compute up here, and it's happening at the same time as this graphics. Some compute right here, and that's at the same time as this graphics right here. So once I've removed all those synchronization points that weren't necessary, now I've actually got asynchronous compute happening, and I've got better utilization of my GPU. The other thing to note is, remember, I was just over 8 or so milliseconds, now I'm 6 milliseconds. So I've actually been able to actually reduce my frame rate by going ahead and utilizing that async compute. But one other thing you can look at here is you can look at this giant section of compute here. I can look down here in my perf markers, and I can figure out what that is. This is this primary raise call, right? And obviously when you select a perf marker, it highlights, or even a command list, it highlights which section you're in. And you can see here that for some reason it looks like I'm not fully utilizing the GPU. I mean, I'm close, I'm 80%, which I know I said earlier is sufficient. But I'm only about 76 or 77% occupied. Well, you can use the tool to actually figure out why that is, right? So remember, we're in our primary raise section. Now I'm going to relaunch the application, and I'm going to relaunch it for, actually going to use it in the full profile and the full synchronous. And I'm going to launch it for frame profiling now. And I'm going to use the frame profiler to figure out exactly where that section is and figure out why am I not reaching the full occupancy that I would have expected there. So I'm going to capture the frame. And again, this is that profiling-centric view that we have. So we show you some of the similar capabilities, but it comes up with a range profiler instantly, so you can see what the profiling looks like. And this is that primary array section, right? So I'm going to click on that. And I'm going to talk more about this in a minute, don't worry. But then I come down here in my summary and I can say, okay, go to my action table, which is basically all of the actions that are in that scene. Here's the draw call, or sorry, the dispatch that's there. I'm going to click on that, and that's going to bring up my API inspector. And so I can maybe look at that, I can maybe look at the shader, but the cool thing is I can look at my statistics view. The statistics view gives you a feel for how is the shader going to utilize the GPU pipeline. Some of it is based on simulation, and some of it's based on exactly the parameters within the shader. And you can see right here that I've got 32 registers in flight in that shader. Well, it turns out, we've got this handy-dandy graph right here that shows you the occupancy of a given shader given the number of registers that it uses. And you can see here, up until about 32 registers, I'm at full occupancy. 64 threads 64 warps can be in flight, fully with the 32 threads. And then all of a sudden at 32, I drop down to 48 warps in flight. Right there, that's my problem, right? I was about 75, 80% occupied, and the reason why was I didn't have enough registers. I had too many registers in use. And you can basically look at that and say, okay, maybe I've got some, for instance, I maybe got some conditionals in there. So I've got a couple of different paths that are going through that shader. That could potentially cause the compiler to have to use more registers. So if you can specialize that shader a little bit more, maybe have two different submissions or something like that, that would allow you to potentially get a higher occupancy in your GPU. All right, some of the other things we want to look at here in the range profiler, one more thing, is look at what we call SOL, or speed of light, or throughput is another word you can use. SOL is kind of like, honestly, it's the soul of NVIDIA, to be perfectly honest, but we're constantly measuring ourselves at what's the peak of what you can do, what's the maximum thing that you can do. And so SOL is basically what is the maximum amount of work that a given unit can do for the amount of time that I was measuring. What's its maximum throughput? And the way you want to interpret the SOL values is basically kind of looking at three different regions. In the lower part is basically if your SOL is medium low to fairly low. The idea here is that if it's a super low value, like 0, 10, maybe even 20%, more than likely, you're not giving the GPU enough work to really get much done. And so that's one you probably don't want to look at, or if anything, you want to look at that as a possibility of adding more work to that unit, because it's really not stressed out that much. When you're in kind of more the 40, 50, maybe even 60% range, the idea there is the GPU had a decent amount of work, but it wasn't able to reach that peak efficiency for whatever reason. There was something that was limiting the throughput from reaching exactly what it wanted to do. And so the idea there is you're going to want to look at, what are some ways that I can tweak my workload to actually reach that maximum throughput. When you're in that 60 to 80 range, it's in some ways a really great thing. It means you're probably in decent throughput range, and you're also giving it a decent amount of work. And those are when you want to start to look at, well, maybe I can try and tweak it just a little bit to gain a little bit extra throughput, or maybe I want to reduce a little bit of that workload, maybe move something from like a shader unit to a texture unit, or move it from a pixel shader to a vertex shader, kind of standard things that we do almost on a daily basis in order to optimize. And then on the top level, you're going to have that 80 to 100%. That's when basically the unit is cranking. It is just hitting it on all cylinders. There's really nothing that's limiting its throughput. So if that is your limiter, if that's your long pole, then you need to go ahead and reduce the amount of work there to try and able to improve your frame rate. So I want to show you a couple of different sections of the scene to give you an idea of how this scene happens to be utilizing the GPU. Now again, Louis is going to do a great job of this later and go into a whole lot more details. I'm just going to kind of hit on it very quickly. So the basic methodology you want to use the range profiler is you want to come in and, it's initially going to come in and basically profile your entire scene. That's kind of interesting, but the problem there is that you've got so many different workloads happening in the scene that making a conclusion based on what's going on there is probably not a wise idea. You've got some sections that are going to be shader bound, some sections that are going to be blending bound, all that kind of stuff. So the first thing you want to do is basically kind of start to look at some of these different ranges and look for the larger ranges. The larger ranges are going to be the ones that have a lot more overhead or a lot more headroom to be able to do potential optimizations. And obviously it represents what's the largest portion, the most expensive portion of your frame. So you can see here, this is my render 1 section that I've got here. And even within the section, it says it's 37% top SOL for texture, and then about 25% on L2. But I could come in here and actually, from within different subsections, different sub-draw calls, I could see quite a amount of variance, right? Like this section right here is 71% L2 SOL versus this one over here, which is basically the G-buffer resolve, that's going to be 46% text. So even within a range, there are times when you want to dig down into an individual draw call, and the tool allows you to do that. And again, this is that G-buffer resolve, and so it makes sense, right? We're going to be reading all those different textures. Some of them are fairly fat textures, 16 bits per channel, and we're going to read all those in, do some nice math, and then finally, produce the end result. A couple other sections I want to show you, give you a better idea of how to interpret some of these values. This is our render shadow map. So this is when it's going to be doing the shadow map pass. It's not going to be doing a whole lot of color and all that kind of stuff. And you can see here it makes sense, right? ZROP is about 20% or so SOL. My L2 is about 10%, and that makes sense, right? I don't expect to see a whole lot of shader work going on. I'm processing the geometry and not a lot on the fragment side. I'm not going to do any texturing or anything like that. So that kind of grokks, right? And then this section over here, this is when it's actually doing the G-buffer pass. And this is going to show a slightly different workload, and this makes a lot of sense too. Now this is when I'm going to be doing all those calculations for all those different buffers for my G-buffer, and it's basically blending bound. CROP is our color ROP, or our color blending unit. ZROP is our Z blending unit. Makes sense, right? I'm going to be blending all those fragments, pulling them all together, and then obviously sending them over to the DRAM, sending them over to the memory subsystem. So again, now I know that these are blending bound. What would you do with that? It depends, right? I mean, if this is what you need to do because you're generating all your G buffers, well, that's what you need to do. That's where you need to spend that time. But if it's shader bound or something like that, that's when you can start to look at some of these other metrics and say, okay, well, maybe I'm stalling because I'm waiting on the texture, which is this long scoreboard. I'm waiting for a read from the texture or something like that. That's when you start to look at some of these other metrics and kind of dig down into the SM unit. Again, I don't want to steal Louis' thunder. He's going to do an amazing job of giving you some great ideas on how you can utilize these counters. And that's it. Thanks a lot.
Right. Thanks, Jeff. So I hope that was a great overview of the features that we have in Insight Graphics. I think it's obviously a lot of really powerful tools that you can use to profile your scene and get the best performance that you can out of it. So some key takeaways from this session. Hopefully this stays with you. Insight Graphics is the next-gen graphics debugger. Powered by RTX, we have DXR debugging. That's an incredibly important part of, I think, computer graphics, right? We're finally at this point where real-time ray tracing is within grasp. I think we've been waiting a long time for this to happen, and at NVIDIA, we're incredibly excited about it. Having the ability to debug the scene that has DXR in it is invaluable to learning how to use that API. The range profiler, I think it goes without saying the kind of depth of information that you can get out of it is incredible. To really take advantage of your GPU, you have to understand to some basic level what SOL is, how to take advantage of counters, and really how to see what those metrics, how they line up to your performance in your scene. GPU trace is the next level of information that I think you need to be able to get the best graphics from your GPU. We liken it to having an NVIDIA Ninja sitting next to you, GPU Ninja, who can give you a lot of really great information about your scene occupancy, your GPU occupancy, and your async compute opportunities. And so to give you a little bit of an overview into NVIDIA DevTools and NVIDIA DevTools graphics, the thing that we're really committed to doing is increasing release frequency. We want to have the tool out more frequently with fixes, with new functionality. We actually have an early access program that we're asking developers to join. This is something where we want to have effectively, a channel where we can get developers builds sooner, so that they can, if something's blocking you, you can get a build that unblocks you. Solving developer pain points is incredibly important to us. We're listening, we're talking to developers on a regular basis. We want to understand the kind of problems you're actually facing day in, day out. Performance is obviously a big aspect there. DX12 is incredibly powerful, and Vulkan as well. It's hard to get underneath the hood of that and understand exactly where asynchronous compute is being used. So we're trying to solve problems like that, but we're very open to hearing about new problems that developers may be facing and see about how we can solve that problem with you. And fundamentally, the tool is about improving developer productivity. So you should never have to waste a moment with our tool. It's meant to save you time. And so it's important for us to have that ability to understand what your use cases are, make sure that the tool is fast, fluid, potentially able to run at all times. One of the things we've discussed is the idea that now that we have a standalone tool, you can give it to your QA department. They can actually go and launch your game or your application with it and be able to take captures and share that with your team, with your graphics programmer. There's visual anomalies. You can actually go and have a capture that you can just save off with your bug report and be able to find that issue. And then somebody can just start the capture up and figure out what's going on. So fundamentally, that's what our tools are about, improving your productivity. I wanted to call out that we actually have a really close working relationship with Microsoft and specifically the Microsoft Pix team. It's been a great and close collaboration with them, and we worked with them to expose a lot of NVIDIA specific functionality within the tool. So work history buffer, i.e. the time activity, is something we help them with. Hardware performance counters. We have a low-level hardware counter library that is basically shared with them that allows them to have that functionality. That's actually what you're seeing on the right there. GPU occupancy viewer. So all the technology that we built for GPU trace was built in a way where we could actually share that with other people. So working with the Pix team to build that into the latest version that they shared with everybody here was really a great experience. And performance warnings. This is effectively performance advice for free, right? Being able to basically just run a capture and see where you can potentially improve your performance by making a few changes is incredibly valuable. Our developer technology team actually helped them, and it was a very close collaboration to get those in. And DXR visualization as well. This is something we've worked with them to expose, so that's something available to them. So, what is the future of Nsight Graphics? What's next for us? In the first half of the year, we're going to be getting Vulkan 1.1 support. In addition to that, Linux support. So a lot of developers have been asking for that, and I think that's going to be great. We have another tool called Linux Graphics Debugger. That's going to be deprecated in favor of Nsight Graphics with the hope that we can have one central tool that you can learn once and use in numerous places. And improvements to the range profiler, and of course GPU trace external release. As I said, right now we have an early access program that we want developers to join so that we can get that feedback really early on. But we're also demoing it here, so you guys should check it out at the booth. And finally, DXR improvements. It's incredibly important for us to have a really solid tool that solves the kind of problems that DXR developers are running into. As happens, it's a technology that I think a lot of people are going to be learning a lot of stuff early on and trying to find ways to apply it to their game and application. And eventually, we're going to have DXR launch titles, right? So we want to make sure that we're addressing the things that are going to slow down their ability to launch. In the second half of the year, we're hoping to have GPU trace for Vulkan. So in the same way that you can find asynchronous compute opportunities within DX12, we want to expose that for Vulkan as well. Pixel history, really cool feature that Jeff showed. We have that right now for DX11 OpenGL. We're going to have it for DX12 and Vulkan. And DXR profiling, incredibly important. If you guys are going to be releasing a performant application that uses DXR, obviously you're going to need to make sure that you can find bottlenecks and limiters and be able to address those. And so we understand that, and we're finding ways to get that profiling capability in place. So what's next? Visit our booth. We have a demo on the floor of Nsight Graphics with GPU trace and DXR debugging, along with a ton of really cool DXR stuff that you should check out as well. Check out Louis Bavois' talk in about 30 minutes to learn more about performance triaging with the range profiler. Watch our videos. We have some really great videos that go in detail in our different features. Join our early access program and get Insight Graphics here. I'll leave the link up for a second if everybody's snapping a picture on their phone right now.
And also, Insight Graphics shipped on Monday, so it's available now.
That's right. Also, I just want to call out that we're hiring. If you stop by our booth, stop by the recruiting station if you're looking for a really great place to work that values really smart people, and you get to work on really cool stuff. All right, thank you.
Any questions?
So are we doing the raffle first, or?
Questions first.
Questions, all right, let's do questions. If you have questions, please walk to the mic over here.
One of the things that I've seen in some of the other graphics debuggers is the ability to, when you're looking at, say, a buffer view, to reformat it as a particular structure type, like, oh, this is a vec4 followed by an ivec4 followed by a uvec4, that kind of thing. Are you looking to do that in the debugger or the Visual Studio Edition at some point?
Jeff, do you want to answer?
Sure. Yes, we've been hearing that quite frequently, and so I can tell you that we are going to up the priority of that one for sure. I can't give you an exact date, but you're probably the third or fourth person that I've heard, not quite today, but in the past 2 days, who have expressed the same thing. So definitely we're going to up the priority on that case.
You mentioned that you're bringing the GPU trace functionality for Vulkan. Will that be the range profiling functionality as well? Because I don't think you've supported that for Vulkan before.
Range profiling for Vulkan is something we want to do in the future.
Okay, is that?
We don't have a specific date on when we want to do that, but it's not going to be in the first half of the year. And ideally, we can get it before the second half of the year, but it's more of a long-term thing. What we're doing right now, though, is we're talking to developers to understand what the priority is on that, because GPU trace can be somewhat of a stopgap to make sure that you guys have some degree of data on the Vulkan profiling
Yeah, that would definitely
front.
be useful, because I don't think there's anything that we have for profiling on Vulkan with NVIDIA at the moment. So yeah, that would.
Yeah, cool. That's right. Yeah. Is Vulkan profiling something that has been a sticking point for you in your development?
Yeah, definitely. And yeah, I develop for Linux as well, so we don't have anything for Vulkan on Linux at all at the moment. So yeah, that would definitely be useful.
Thank you for your question.
And if I can, if you develop on Linux, the latest version of Linux Graphics Debugger, which we shipped 2 or 3 weeks ago, does support Vulkan.
Okay.
Yeah.
Well, sorry, real quick. I think we have to do the raffle first before the next question.
All right, next question.
Hi, I saw the logos for Oculus and SteamVR. I was wondering if there are any specific VR features or workflow complications.
We do. There's a hidden slide with VR Inspector. We do have some VR inspection capability, and it's something as well that we're trying to listen to developers understand where they're running into issues and trying to develop tools to improve upon that. If you have specific use cases, the email address is up there, by the way. Feel free to send it our way, and we can start a discussion about it offline.
Okay, and I was wondering particularly the C++ captures. What would those look like for VR applications?
Those are fully supported. It generates and everything. It puts all the either OVR or code in there so that it will replay.
Oh, cool. Thank you.
Yep.
Thank you. Any other questions?
Wonderful.
All right. Thank you very much.
Thanks, everybody.